Hi, everyone. Welcome to week 13 of Astronomy 236. This is our second lecture bite, where we'll be talking about the future of planetary systems throughout our galaxy. So, over the last couple of weeks, we've gotten a basic understanding of how we got here, or really the entire semester has been the story of how we got here. But now, this last week, I want to talk about where are we going to go from here, and in particular, what will happen to the solar system and planetary systems in general in the future. What happens to planetary systems after their stars run out of hydrogen fuel and leave the main sequence? Here's a reminder of what happens to stars in general when they run out of their nuclear fuel and leave the main sequence. So up here, for the most massive stars, they will eventually burn heavier and heavier elements until they no longer can. Their cores will collapse into a supernova that will either leave a black hole for the most massive stars or a neutron star for less massive stars. For stars like our sun, they will eventually swell up into a red giant, become very, very large, then shed off their outer layers, leaving a planetary nebula behind, and then eventually cool into a white dwarf. And then for the smallest stars, stars that are smaller than about 60 or 70% of the mass of the sun, they will eventually just completely convert into white dwarfs. But they actually have never done this because our universe is too young for this process to have ever taken place. So we think this is what's going to happen, but this part should be considered hypothetical. So for the most part in this lecture, I'm going to focus on the highest mass stars and these medium mass stars like our sun and talk about what happens to their planetary systems. Here's a pie chart showing what will happen to the stars that host all of the planets that we know about today. So we know of over 4,000 planets, and about 99.7% of them will eventually become or be orbiting stars that will turn into white dwarfs. Only a very small fraction of the stars that we know to host planets are massive enough to become neutron stars instead, or already are neutron stars, and I'll get to that in a second. And none of them that we know about yet are massive enough that they will eventually turn into black holes. This is just a statement of how rare really massive stars are. The lower mass the star is, the more common it is. And the ones that are really, really massive, the hugest ones that will eventually turn into black holes, just turns out they're very, very rare. And it's also hard to detect planets around them. So I'm going to start off by talking about these high mass stars that become neutron stars or black holes. Here's a reminder of what a neutron star is. It's a very, very dense, small object. It's about 10 kilometers in diameter. So compared to the skyline of the city of Chicago, you can see a significant amount of curvature in this neutron star. And one class of neutron star that are particularly important for exoplanet studies are pulsars. So remember, pulsars are neutron stars that are rapidly spinning, and they have a beam of radiation that comes out of their poles, their magnetic poles, that sweeps across the sky. And if we happen to lie in the path of one of these beams, we will see that as a short pulse of radio waves coming at us every time the star rotates. And this rotation can be very fast. It can happen on timescales of hundreds or thousandths of a second. Some of these pulsars have spin rates of a millisecond. So every millisecond they spin around, every second they spin around 1,000 times. So one of the ways that we can investigate pulsars is by pulsar timing. So I want to show you a demonstration of what this can look like. So over here on the left, I'm showing a pulsar. And you can think of it like in this previous slide here, where it's spinning around and seeing a pulse of light. But I've just simplified this light to look like a little red laser beam that's being shot every so often. It has the same effect as it would if it were just a beam that was being swept around the sky as far as our Earth is concerned. So this pulsar is shooting a beam of light at Earth on a regular basis every couple of seconds, as you can tell. So when the pulsar is standing still, you see that this pulse arrives regularly. But what if the pulsar suddenly were to move closer to the Earth? And if it moved like right now, then you would see that there's a shorter gap in between the pulses for that one pulse. This is called the Romer delay, or the light travel time effect. Because the pulsar is sending something at the speed of light, if the pulsar is closer to Earth, it takes less time for that pulse to get here. So even if the pulse is being sent regularly on the same schedule, we will receive it in a slightly different time with a slightly different delay in between each pulse, because it will have taken less time for it to travel to us. We can use this to our advantage to look for very small motions of pulsars. As planets pull on their stars, whether these are main sequence stars or pulsars or neutron stars or anything, they will tug that star very slightly closer to us and very slightly away from us, depending where they are in their orbit. And using pulsar timing, we can measure these changes in the pulsar's position with extreme precision. So here is a plot of the times of, or the apparent period of a pulsar. So similarly related to when the pulses arrive for a pulsar called PSR B1257 plus 12. And what you can see is that this pulsar seems to be changing its period. It seems to be changing the amount of time in between each successive pulse. And it's doing this in this fairly repeatable way. So it has these slow wiggles up and down that, if you carefully look, it turns out that these are corresponding to sinusoids. So when you look at the sinusoid, it's due to the motion of the pulsar back and forth. So over time, the pulsar seems to be moving back and forth away and towards us in this semi-regular way. The reason for this is because there are planets orbiting this pulsar. This was actually perhaps the very first system of planets that was ever confirmed. This, you can see the paper was published in 1992, even before the discovery of 51 Pegasi b. So pulsar planets were among the first ones to ever be discovered. These are really weird objects. There are 3 planets in the system. They're relatively small. One of them is even as low mass as our own moon. And they orbit around a pulsar. And remember, pulsars are neutron stars, which formed during the core collapse of a massive star. So these planets would have been forming in a region that was just recently blasted by a supernova. So that begs the question, could these planets have actually survived being blasted by a supernova? And this has been something that scientists have been thinking about for the last 25 years. And the general consensus is probably not. These planets probably would not have been able to withstand the supernova blast, this extreme explosion very close by. So instead, it seems possible that these planets formed after the supernova, from the remnants of that supernova. So they formed out of the leftover debris from that explosion, which then recoalesced into a disk around the pulsar and formed planets in a very similar way to the way planets must have formed originally in protoplanetary disks, but in this second generation of material, the debris from this explosion. So one of the questions that's pretty interesting to ask is, why didn't the pulsar planets kick off the exoplanet revolution? Why did it take 3 more years, when 51 Pegasi b was discovered, for exoplanet studies to really kick off? And it turns out that the answer is a little bit that nature was just unkind to us when it came to pulsars. And there are 2 things that make it hard to find planets around pulsars and hard to learn much about the planets around them. Number one is that pulsars are rare. Only about 0.6% of stars are massive enough to become neutron stars or black holes. So there just aren't that many pulsars around to look for planets around. And number 2, it turns out that the planets orbiting pulsars are rare themselves. After almost 30 years of searching, only a few other planets or candidate planets have been found around pulsars, perhaps smaller than the number you could count on one hand. Compare that to the tremendous results that we've seen searching for planets around stars like our sun, where we have found thousands of them in the last several decades. It just turns out that pulsar planets are a little bit too unusual and a little bit too much of a rarity for them to really have kicked off the exoplanet revolution. And it turns out that planets around black holes suffer the same problem. We don't know of any planets that are orbiting black holes so far, even though we think that probably they could exist in the same way as the pulsar planets do. There's a couple of reasons for that. One of them is that black holes are even more rare than neutron stars and pulsars. They also don't have as convenient methods for us to search for planets around them. We can't just measure the timings of the pulses from pulsars super easily. We can't do that for black holes, so we have to use other methods. There is one tentative way that we might be able to do it, though, which is through transits. Now, of course, black holes don't emit their own light, they're black, but they do have typically accretion disks of hot gas around them that emit light. Often this light is measured in X-ray wavelengths because this gas is so hot and is being slammed so hard into other gas particles that they have these very high energies and these very high temperatures. So if you were to look for transits of these accretion disks like this, you might be able to find evidence of planets orbiting around black holes if you got lucky. And earlier this year, there was a very tentative candidate planet discovered. So here's what it looks like. This is the light curve, the brightness of the star in X-rays on the y-axis, and the time in kiloseconds or thousands of seconds on the x-axis. And you can see that there is this dip in the brightness of the star. It blocks essentially all of the light from that accretion disk, so it must be relatively large. And it turns out that this is actually in a different galaxy. This is in the Whirlpool galaxy called M51, and this is the source right here in X-rays. This is not necessarily known to be a black hole. We don't know if the thing that the X-rays are being emitted from is an accretion disk around a black hole or another neutron star. So it's possible it's not a black hole, and perhaps, odds are equally likely that it's a black hole or a neutron star. It's also not clear that it's a planet because it could be too large to be a planet. We don't know. It'll be very difficult for us to find out. But I wanted to show you this just to show that there are ways that we might eventually find planets orbiting black holes. And if we do, that would be a really exciting discovery. So I'm going to spend the rest of this lecture talking about low mass stars that eventually become white dwarfs. It turns out that this is a much more fruitful area to look, just because stars that become white dwarfs are so much more common than stars that become neutron stars. And we have some convenient ways that we can look for planets and evidence of planets around white dwarfs as well. So as a reminder, here's what will happen to our own solar system when our sun runs out of fuel. Here's our sun in the center. When it runs out of nuclear fuel, it will swell up to be about 100 or 200 times its original size. And unfortunately for the inner planets in our solar system, that's not good news because it will actually expand beyond their orbit. Mercury and Venus will definitely be engulfed by the sun when this happens, and it's possible that Earth will be as well, although there are some uncertainties in exactly how far the sun will expand out and what will happen to Earth's orbit as it does that. So Earth may survive. Regardless, it won't be a great place to be, because if it does survive, it will be barely skimming the surface of this giant star and probably will not be a very pleasant place to live. And then once it's finished burning all of its hydrogen fuel and burning all of its helium, the sun will shed its outer layers and leave a tiny white dwarf core in the center of the solar system. Because the white dwarf loses mass, it loses its outer layers, its gravitational pull is weaker. And therefore, all of the planets that are orbiting around it after it becomes a white dwarf, the ones that survived the initial expansion to becoming a giant star, a red giant star, all of those planets will move outwards as well because the gravitational pull of the star is less, so they will be essentially less tightly bound. So all of the planets further out than about Mars will smooth out slightly in their orbits. but they should survive. And in fact, we have pretty good evidence for planets surviving this process far away from their star. So here are the two systems that we know about today. So this is a white dwarf called WD 0806 661 right here. And here is a blob over here that appears to be a planetary mass companion. It has a mass about 8 times that of Jupiter, and it is cool enough, or it is massive enough that it's retained some of its original heat to the point where it can be imaged with Spitzer. So this is an image from the Spitzer Space Telescope in infrared light looking for heat from this planet. And we can see that this planet here seems to be traveling along through space along with this white dwarf here. As you can see, though, it's very far away from it. So the orbit is really, really, really far out there. There's also evidence for 2 planets around a white dwarf called NN Serpentis. This white dwarf is actually a binary star. It has a nearby star about smaller than the sun that orbits very close to it. And what you can do is you can watch how those 2 stars orbit each other and look for small changes in those orbits. And we've actually seen similar the small changes like that. So here are the changes to that orbit plotted over time. So this is the change to the orbit in seconds. So only a few seconds are making this difference. But over time, we've seen that this binary star, NN Serpentis, does seem to be getting tugged back and forth by 2 different planets orbiting around. So we know of a couple of planets that orbit around white dwarfs, but for the most part, they all orbit far away from the white dwarfs. So one of the questions that we'd like to know is what happens to planets after their star becomes a white dwarf? Can they ever come back close to the white dwarf where we think that anything that originally orbited there should have been engulfed when that star expanded and became a red giant? And the answer is it seems like there are planets, or at least planetary material, that does come back in close to their star after it becomes a white dwarf. And some of the evidence we see for that is in what we call metal pollution. And I'll explain what I mean here. So here is a spectrum of a white dwarf, and you can see lines in the spectrum. These are due to elements like hydrogen. But then there's also this one little line here for calcium. And this calcium line is evidence that a planet must have come in close to the white dwarf. And I'll explain why right now. So it all stems from the fact that white dwarfs have very strong gravity close to their surfaces or on their surfaces. Even though their gravity further away from the system is weaker because they lost some mass, they have such compact areas, they have such compact volumes that if you get really, really close to their surface, the gravity is very strong there. So this is the formula to calculate the strength of gravity at any location, or how much gravity will cause something to accelerate, or how much gravity will tug on something in a particular location. And the way you do it is you divide essentially the mass of the object, which in this case is similar to the mass of the sun, a little bit smaller because it's lost some of its outer layers, by its radius squared. It's the radius that really does it here, because the radius of the white dwarf is very, very small. If you divide by that number squared, you get a very, very large strength of gravity. So even though the white dwarf is only half as massive as the sun, on its surface, its gravity is 10,000 times stronger than the sun's gravity. And when you have strong gravity, you can get some interesting effects. And the main one that matters here is that strong gravity causes heavier elements to sink down towards the core of the white dwarf. So the way to think of this is kind of like panning for gold. If you ever heard of panning for gold, this is one of the ways that people used to search for gold back in the 1800s. They would go out into a river. This river potentially has gold flecks mixed in with the sediment in the river bottom. They would scoop up a little bit of the sediments into a pan that looks like this. They would scoop some water into it as well, and then they would shake that pan around. And in the process of doing that, the heavy stuff will sink to the bottom faster. In this case, gold is denser than rock and sediment, so the gold will sink down to the bottom of this pan. the rock and sediment will stay higher for a little bit longer. So what you can do is, if you're skilled, you can skim off the top, get rid of the rock and sediment, and keep only the gold in your pan. This exact same process is happening on white dwarfs. The gravity of a white dwarf causes heavier elements, things heavier than hydrogen and helium, to sink down to the core where we can no longer see them in the spectrum. So if you take a look at the spectrum of a white dwarf, you would expect to see only hydrogen and helium, because on the surface of a white dwarf, you expect to have a thin layer of hydrogen, a thin layer of helium, and then everything else, heavy stuff, sink down to the core. And indeed, if you do look at spectra of white dwarfs, that's what you see. So here's a spectrum of a typical white dwarf. You can see that there are only strong lines caused by hydrogen. There are no spectral features. There are no fingerprints of any other elements in the spectrum besides hydrogen. But as I just showed you, that's not always the case. Some white dwarfs do have evidence of the fingerprints of elements other than hydrogen in their spectrum. So in this case, this white dwarf has evidence of calcium in its spectrum. In this case, there's a lot of other elements. So looking at this white dwarf spectrum here, you can see magnesium, silicon, helium. I think there's an iron in here somewhere, calcium. So all of these elements should be sinking very quickly to the core of the white dwarf, but we still see them on the surface. So the only thing that we can conclude is that these elements must have been put here recently. So how could a white dwarf be sprinkled with these heavier elements? So one thing you might think of is that perhaps this white dwarf is traveling through space, and it goes through a cloud that happens to have heavy elements like calcium, magnesium, or silicon in the cloud. And as it goes through this cloud, it would pick up some of those elements, and we could see it on its surface before they settled down to the center of the white dwarf. This is something that astronomers thought about in the 1970s and the 1980s. And when they thought about it, they thought it was a possible idea, but the numbers just didn't work out. For one thing, there just wasn't enough of these materials in clouds to cause the amount of materials that we see on these white dwarfs. For another thing, it turns out that these white dwarfs, if you imagine that these white dwarfs are getting all of these materials going through clouds, you would expect that white dwarfs in similar parts of space would have similar things on their spectrum, but that wasn't necessarily what we saw. So this explanation didn't really work. Things started to make a little bit more sense, though, when astronomers realized that many of the white dwarfs with these mysterious spectral features, these mysterious lines caused by elements that should not be on their surfaces, also had evidence of bright light coming in the infrared from nearby. So what does this mean? If we look at the spectrum and we see that the white dwarf appears to have a black body shape, but then there's another component, another area of another thing that's emitting light in the infrared, that must mean that there's another slightly cooler object nearby that's emitting light. It's still warm, it's still producing a good bit of light compared to the white dwarf, but it's definitely cooler than the white dwarf itself. If you take a closer look at this infrared light, you can see that it has a spectral feature at about 10 microns, which is consistent with what we expect for rock and silicates. So there's evidence that these white dwarfs that happen to have spectral features in their atmospheres of stuff that was recently deposited there that shouldn't be there otherwise, also have rock orbiting nearby in these dusty debris disks. We think this rock has been pulverized and crushed up. And finally, when you look at the elements that are in white dwarfs, if you take these spectral features and you measure how much magnesium, how much silicon, how much calcium is in this white dwarf, and compare it to what's in other bodies, it turns out that the amount of stuff on these white dwarfs is very similar to the ratios of elements that we see in rocky objects in our solar system. So on the y-axis here, I'm showing the ratio of different elements to that of silicon. So how much there is of oxygen or sodium or magnesium or aluminum compared to silicon. These black dots show what's in this white dwarf. And these solid lines and dotted lines show what's in rocky bodies in our own solar system. So it turns out that the composition of whatever has been dumped onto this white dwarf recently is very similar to the composition of rocky material in our own solar system. So the idea is that these white dwarfs that show these elements in their spectra have recently eaten planets or eaten rocky material, say an asteroid or a comet. We see the remnants of that asteroid now scattered onto its surface, where it's going to stay there for just a short period of time before all of those elements slowly settle to the center out of view from our spectrographs. So this is pretty startling because it turns out that this is very common. About 25 to 50% of white dwarfs do seem to show this type of planetary accretion, this type of planetary cannibalism. So how could this be happening? We know that when a white dwarf forms, the red giant will clear out all of the inner parts of the solar system. So these rocky bodies must be coming from far out in the solar system. What we think happens is that when the white dwarf loses its mass, its gravity weakens, causing all of the orbits to shift outwards, as I said. But when this happens, the gravity is weaker still compared to the planets. So the planets can now tug on each other more than they were able to beforehand. When the planets tug on each other, they can start to change each other's orbits. And in some cases, you can shoot small objects, small planets, small asteroids very close to white dwarfs. And if they get close enough, these objects can end up being disrupted, torn apart by the strong gravity of the white dwarf very close to its surface. Here's an image of this kind of thing happening to a comet in our own solar system. You can see this comet essentially fragmenting and being torn apart into many different pieces. Once the object has been disrupted, it gets pulverized, it collides in with itself and ground down into dust, forming this disk. And then that disk eventually streams material onto the white dwarf, where we can then see it in the spectrum. And we can see the evidence, the fingerprints of these planets illuminated on the surface of the white dwarf. We've also seen this process in real time because we've seen transits of disintegrating objects. So here's a typical transit light curve with the brightness of the star on the y-axis and the time on the x-axis. And you can see in this case that there's a sharp dip in brightness, but it's a slow recovery. This is different from the transits I've shown you before, because usually the transits that I've shown you before are symmetric. They have a sharp decline in brightness, a flat bottom, and then a rapid rise in brightness again. This case is different though, because instead of a round object going in front of a round object, we have an asymmetric object going in front of a round object. So you can think about this almost like a comet, where you have this dense head of material that's causing a sharp decrease in brightness when it moves onto the star, and then a less dense, diffuse tail of debris trailing behind it that takes a long time to slowly fade back to its original brightness and no longer block any of the light of the star. So it really does seem that in this way, white dwarfs occasionally eat parts of their own solar system and eventually hide the evidence in their cores where we can no longer see them. But after watching all of this, so far we've only been talking about planets that are in the process of getting destroyed. Can any planets actually come in and survive this process? Can planets come back close to a white dwarf where they originally were found? And the answer, it looks like maybe yes as well. So here's a very recent discovery. This is something I worked on from the TESS mission. This is a light curve from the TESS mission, which we talked about a couple of weeks ago, showing a transit event around a white dwarf star. After finding this, we took a closer look and used a larger telescope on the ground to get a really nice measurement of the brightness over time. And this is what the transit looks like. So one of the things that you'll notice immediately about this transit is that it's very deep. More than 50% of the star's light is blocked compared to the very small fractions of light that we saw being blocked when planets went around stars on the main sequence. That's because white dwarfs are very small, so even a relatively small planet can block a very large amount of light. In this case, it turns out that there's something about the size of Jupiter orbiting around this white dwarf and blocking its light from us every 1.4 days or so. But unlike those light curves I was showing you before, this light curve looks totally symmetric. So it looks like it could be an intact planet rather than one that's being disrupted. When we try to figure out what the object's mass is, though, it's a little bit tricky. When you have something the size of Jupiter, there's a large range of possible things that it could be. There are planets that are about the size of Jupiter, brown dwarfs are about the size of Jupiter, and even some very low mass stars are about the size of Jupiter. We would love to know whether this object really is a planet or if it's something else, like a brown dwarf or a low mass star. Usually the way we would do this is by measuring its mass using the radial velocity technique and looking for the wobble of the star as the planet goes around in its orbit. But it turns out that it's impossible to do this for this particular white dwarf. This white dwarf is really old. It's about 6 billion years since it became a white dwarf. It's cold. It's cooler than our own sun, even though it started off very blindingly hot because it was the core of a star like our sun, where everything in the core was really close to the nuclear furnace. And one of the characteristics of very old and very cold white dwarfs is that they have no strong spectral lines. So we can't actually measure the velocity of the star moving back and forth because we can't see where any of those spectral lines might be. So instead, we have to figure out how massive this object is by seeing how bright it is. If it's a planet, it should be fairly faint because planets don't emit their own light and they don't hold on to much of their original heat. If it's something more massive, like a brown dwarf or a star, then we should see some light coming from it. But when we looked, again with the Spitzer telescope, which looks for light in the infrared, where we might expect for heat to be coming from this planet, we saw nothing. So it turns out this really does seem to be likely a planet orbiting close to this white dwarf star. So planets really can move in after the white dwarf formed and come back into a close orbit, even though they weren't able to be there originally. Because if they were there originally, they would have been engulfed by the red giant when it expanded. So here's a view of this system to scale. And in this case, the white dwarf is here. It's much smaller than the planet over here because white dwarfs are about the size of Earth and the planet is about the size of Jupiter. And this is the size of its orbit. So it's actually a very close orbit. If I were to replace this white dwarf by the sun, it would look something like this. So this planet really is hugging its host star closely. And as I said, if this were the way it was before the star became a white dwarf, this planet would have been engulfed very quickly when the star expanded and became a giant star. So originally, this planet must have orbited much further away from where it does now. In fact, it must have orbited further than about the orbit of Earth, at about 1 astronomical unit away from the star. An astronomical unit is just a fancy term that astronomers use to describe the distance between the sun and the Earth. So originally, this planet must have orbited somewhere out here and then moved inwards after the star became a white dwarf in order for us to see it where we see it today. So how could this have happened? How could this planet have moved inwards? Well, one way to explain it is if the planet orbited very far away from the star, and then right as the star was about to lose its envelope, was engulfed by it. This is called a common envelope scenario. And in this case, the planet spirals inwards through the star's outer layers as they're being lost, and eventually contributes to those layers being blown off. It kind of looks like this. So you can see the planet in green is now spiraling inwards towards the star and blasting off the outer layers of the star and eventually ending up in a very close orbit like we see today. It turns out that this is really hard to make work for WD 1856b, though. In order to survive being inside the star, you needed quite a bit of heft, and probably this planet just isn't heavy enough to do it. It would probably either be ablated, blasted away by the heat from inside the star, or it just wouldn't have enough energy to get rid of all of the outer layers of the star and would just spiral into the core and crash into the white dwarf. So this probably isn't the explanation. Instead, perhaps a more likely explanation is that this planet formed by a process called high eccentricity migration. So what this means is that somehow the planet was kicked onto a very highly elliptical orbit, so that it started out very far from the star, but then comes very close in every time it goes around. So here's what that might look like. Coming in very rapidly on its highly elliptical orbit, the planet would get very close to the star. And in fact, when we get close enough to the star, that it would be stretched a little bit. Now, when the planet gets stretched, it loses a little bit of energy. This is very similar to how when you drop a tennis ball from a height, it will bounce back up, but it won't bounce back up nearly as high as it did originally. So the same thing happens with the planet. When you send the planet close to the white dwarf, it will be stretched. But because it's stretched, it's losing energy in that process, and it won't come back nearly as high as it did originally. And eventually, the tennis ball will bounce and bounce and bounce until it no longer bounces, until it comes basically down to the point where it just rolls along the ground. And eventually, the planet in this scenario will spiral inwards and inwards and inwards until it orbits very, very close to the star. One of the ways that you could get the planet coming in so close is if you had gravitational interactions descended on such a highly elliptical orbit. So those interactions could be from other planets in the system. We don't know of any other planets in the system yet, but it's possible there are some that we just haven't detected. It's also possible that this planet could have been sent in by gravitational interactions with two other stars that orbit in the system. So here are two stars that orbit around the white dwarf in the planet called G229-20A and B. These two stars could have been the catalyst for sending this planet on its journey and sending it into where we see it today. So I wanted to leave you with one final thought, which is this is what the system looks like to scale. It turns out that white dwarfs do have habitable zones themselves. White dwarfs still emit light. They're still glowing from the leftover nuclear heat from their star's furnace. And if you get close enough to the white dwarf, even though it's very faint, you could be warm enough for liquid water to exist on your surface if you were a rocky planet. The problem has always been whether or not you could get a planet here, because we know that anything this close to the white dwarf would have been engulfed when the star evolved into a red giant. But in the case of WD 1856b, it made this journey and it got almost close enough to be in the habitable zone. So if this planet could survive the journey close to its white dwarf, maybe a smaller planet could do that as well. And maybe it could get to the habitable zone where it would be a potential place for life to exist. If we found such a planet around a white dwarf in its habitable zone, we could study it with the methods we've talked about on this planet to search for life on this planet. Using transmission spectroscopy, we could look for wavelengths at which its atmosphere is more opaque than others, and potentially be able to see if there are biosignature gases in its atmosphere. So we would be able to look for things like oxygen and water vapor and methane. The reason why this is potentially exciting is because when you're trying to do this with transmission spectroscopy, the smaller the star, the better. And that's because for a planet with a given size, the smaller the star, the bigger the signal that it produces. And white dwarfs are really small, so they take this to an extreme. An Earth-sized planet blocks a lot of light from a white dwarf and causes really big signals, which are easy for us to detect with our instruments. So if we were able to do this, if we were able to find a planet in the habitable zone of a white dwarf, we could search for biosignatures relatively easily with the James Webb Space Telescope, which is supposed to launch next year. This is a simulation of the kind of data we would get if we looked at a planet in the habitable zone of a white dwarf like WD 1856. In only 25 transits, which is about 3 hours of observations that would be spread over the course of about a month, we could confidently detect several different biosignatures. We could detect things like carbon dioxide, methane, ozone, nitrous oxide, nitrogen, oxygen in the atmosphere. All of these things would be possible if we could find such a planet. So it's possible that white dwarfs could be a place where life could survive long after their host stars died and ran out of fuel. Even after their host stars died, these systems could still host life. And number two, this could be a shortcut for us detecting biosignatures if we're able to find a planet where we might be able to look for them. So hopefully in the future, we'll be able to identify white dwarfs using the Gaia mission, which we've talked about. We'll be able to search for planets using TESS, and then we'll be able to use the James Webb Space Telescope to look at the atmospheres of those planets and see if we can detect biosignatures around these other stars.